So when you start engage, you get this form. And the only thing you can do is click the load button. So that will go and get all the config files and bring them in and show you what it actually saw. There are 3 config files we're interested in. One is a scenario file called xjam.dat. Another one is a missile model, which has several names, but if you look in the input directory, you'll see the names there, missile model.dat kind of thing. And an antenna and radome configuration file. Those are the 3. And then there are some other files like a config file for Invicta and a config file for the reacquisition estimator and a config file for the passive range estimator. But the 3 main ones are the scenario, the missile, and the antenna and radome. So when I click load, that's what we see. So let's go quickly just around from top left to bottom right, but what these controls are, in simple terms, what they do. So at the top left, we have randomization options. There are 4 options for randomization. The first is to randomize the missile and scenario only. Okay, so let's talk briefly about that. If we click the model button, up comes a little teeny form, and you can look at different configuration forms like the antenna and radome and the sightline filters. Let's look at the secret processing. That's a complicated looking one. But they have one thing in common. There's a left edit box and a right edit box. There's a nominal value and a variability. And the variability is generally like %, or some of them are in dB. And if you click, choose these values, and if you choose, then choose close, and then choose missile and scenario randomization, those things, on every time you do a run, it'll pick a new value for each one of those parameters within the bounds that you specify. If you choose antenna only, then here's the antenna model. That's got a bunch of parameters on it. Same story, only when you're randomizing just the antenna, then the missile parameters are all nominal values, but the antenna itself, special case, antenna and radome, they're randomized like this. We're going to come back to the antenna and radome model in a minute. And then there, of course, is an option to randomize them both. But we're using none. As we can see, if we click load, it goes right back to where it was. Run type. We could use an angle step response to look at our seeker design, because you really do have to become a missile designer. You can't just randomly pick, I'm going to use an inverse cascade antenna. I'm going to use a elevation guided autopilot. I'm going to use they all have to make sense, just as though you were building a missile and testing it in a lab before you sent it out of the factory with quality assurance and things going to hit something when you fire it. We could do a angle step response, or we could do a ramp response, or we could use ECM, which is normally what you think we'd use it for. Lorenz run, look it up, doesn't matter. The essential idea is, suppose you're doing some, you do an interesting run and you say, well, and it was some randomization was turned on. So we don't know exactly, well, we can find out. We don't know exactly what the software chose for all in-play parameters. But if you click that Lorenz run, it will go back to the immediate previous run. It'll recover the random number seed. So you can have exactly the same run again. But you could change a nominal parameter. So you could see what happens if we change the polarization sweep rate by 1 degree per second. Otherwise, an identical run. So you could change 1 or 2 things under certain circumstances, or just change the propagation model, or remove propagation. So that's what the Lorenz run thing is. Termination criterion. There's 2 choices. Range, time, it'll stop after 30 seconds, or range, it'll stop after, when it gets to within 10 meters, let's say, of the downrange position of the ship. Now, there are several reasons for termination criteria, and here they all are. One reason is the antenna deflection. The antenna got pushed so far off boresight that we're not interested in it anymore. And there's a parameter on one of the forms that you set. Right now it's set to like 90 degrees, so it is never going to terminate at that. Another possibility is time, we just talked about. Another is range. Another is impact. If it hits something, that's it, end of run. If it ditches, if the missile misses the target and keeps flying, and eventually it'll run out of fuel, which is another parameter, it'll just ballistically fall into the sea. And when it hits 0 altitude, end of story. And another option is heading. If the heading error becomes too large, we say we're not interested in running this anymore. So the main reason for having most of these is that if you were doing batch runs, like 1,000 runs or 2,000 runs, and you just leave this thing run for several days or even weeks, then you don't want to be coming back wasting a whole bunch of time on runs, gobbling up execution time on things that are not important. Like, we're not interested in thinking it's developed a 40-degree heading error. We're not interested anymore. There's no need for it to take another hour to finish that. Okay, so where are we at? Termination criteria. Multipath, that's an easy one. So we can enable multipath or disable multipath. And when you do, you see this little, icon, visual cue that says that's not turned on. And if it's on, we have a choice between curved earth model or a sea swell model. And the difference between those two, if we click on this picture, boom, a picture comes up and shows that a curved earth model looks like this with these surface waves on it, and a sea swell model looks like that. So that's the difference. And then the curved earth model, we get a single specular reflection, and with a sea swell model, we get multiple reflections. I think this one is more realistic, but it's more time consuming, like much more time consuming. If you had 5 or 6 reflection points on the sea surface, then you're basically running the curved earth model more than 5 or 6 times. You got to find, because you have to find those reflection points and then do the math. But the curved earth math is really slick. It's really fast. It runs really quickly. And you see that it has multiple reflection points. So I wanted to show, give the user some sort of confidence that they understand what's happening, that the software is operating correctly. So the runtime animation form shows you where the reflection points are on the sea surface. So here's for the curved earth propagation model, we see there's only one specular reflection point, but for the sea swell model, there are multiple ones. And these are at the crests and sometimes the trough of the sea swells. And if you change the sea swell wavelength, those things move farther apart. And as you change the altitude, it's kind of fun to watch these little crosses move in and out. So, and also I look at it and I think it intuitively makes sense to me, So I think, of all this math and this piles and piles of code, it looks like it's running correctly because we see this picture. So if we have the curved earth or the sea swell, either one, the first parameter to be aware of is wind speed. Now this affects the surface waves, the size of the surface waves, which affects the reflectivity, which affects null depths, which affects fade rates, which affects ECM effectiveness, operations for a jog detector, for example. So we would be interested in surface roughness. And if we have the sea swell model on, then there are 3 other parameters to choose. We have to choose peak amplitude, wavelength, default is 800 meters. Like sea swells are slow, long period, low amplitude waves. They're not what you see from the deck of a ship. This is what you see from an airplane maybe. And then the surface waves are running on top of those. And the last parameter here is that you don't want to be calculating, as I found very quickly, you don't want to be recalculating propagation every time step in a simulation. So instead, when the missile moves a certain distance, we recalculate propagation. And this is what that bottom parameter is, 10 meters. It's pretty small. Is that the right number? I don't know. But you could actually do a study with this. You could put it at 10, 100, 50, 25, and do a bunch of runs and see what difference it makes in terms of execution time and in terms of results. Okay, back to the top here. Autopilot, that's reasonably important. So look, we can enable forward motion. Oh, look, we stopped forward motion, and we get an error message saying, hey, you said you wanted to stop at a range criterion, but if the missile isn't moving, that doesn't make any sense. So if you click OK, it goes back to time. Fly out sample rate right here. Set at 50 hertz. This is the data recording rate in hertz. So as the missile is flying along and the simulation is running, it's generating data very, very densely to solve the differential equations, but it's only logging them at this rate. Then there's something different, which is the jammer update rate. That's not a sampling rate. That's how frequently does the jammer update itself. It looks at the world, it does something. It looks at the world, it does something. Update rate. And it logs, both of them are logged at 50 hertz. So the 50 hertz is the data file you get to look at the end. The jammer update rate is like while we're doing the simulation, how frequent. Probably that's clear. Include decoy. Yes, you could have a decoy. An offboard decoy. Okay, so let's move on to emitters. The software, I had to distinguish between 2 ideas. There's ships and emitters. And an emitter might have a ship associated with it or it might not. For example, a decoy could have an emitter, but it doesn't have an RCS. Well, you could associate it with a ship if you wanted to, but not necessarily. So emitters and ships, that's an idea. So emitter types, you could have it could be blanked, it could be a beacon, or it could be ECM. And if it's ECM, there are a bunch of types: cross pole, AM cross eye, polarization cross eye, double cross. Do not mess around with those. Two element countermeasures. They're really interesting and cool. This software is not verified for those. The hooks and features are in there, but I don't play with that anymore. To me, it's cross pole jamming or beacon would be the things you're interested in. But if you're interested in cross pole jamming, then we look in this little box right here. So we have a clockwise sweep limit, a counterclockwise sweep limit. What does that mean? Well, if you click polarization definition, it shows you what the definition of clockwise and counterclockwise is. Looking out of the antenna, see here, clockwise is in this direction, looking out of the jammer antenna toward the radar, or toward the threat, whatever it is. So clockwise limit, counterclockwise limit, clockwise rate, counterclockwise rate. The start polarization is the clockwise limit or the counterclockwise limit. We also have a start direction, clockwise or counterclockwise. There's also a rest angle. Might be at 90 degrees, might be at 45 degrees. And how long do we stay there before we get going? Okay, moving up to the top here. Now we're talking about more or less more of the jammer. For example, what's the transmitter or the emitter downrange distance from the missile? 10 kilometers right now. What's the jammer transmitter cross range position? 0. So picture a world coordinate frame here. That one would slide the ship left and right, up and down, cross range position. And the downrange position is the distance, the start range of the missile from the ship. Ship's at the origin. Ship 1 is at the origin. So that's what that means. Jammer transmitter height. Okay, for the CPF, we'd have it at about 15 meters. Looks like 14.5, 15 meters. Jammer transmitter half power elevation, half power beam width, set at 15 degrees. And that's for propagation, because there's a look angle, a direct and the indirect path does look down through the jammer transmit antenna, so we need to know what that half power beam width is so we can make the propagation model as realistic as possible. Jammer response time. Well, this is how long it takes for the jammer RF to turn on. That's not the same thing as the polarization arrest delay. So when the seeker turns on, these many seconds will pass before any RF comes out of the horn. That could be like representing a TSDB lookup time, like it might take a couple of seconds to find an emitter in a database before you know what to do. Boom, it can go, so that's possible to represent that. Jammer transmitter antenna gain, 20 dBi. Jammer antenna receive antenna gain. That's important because we are interested in jog detection, right? So how much power are we getting from that seeker? Seeker's configured. It's got a transmit antenna gain. It's got a transmitter power. It's a certain distance away. Here's the propagation. But what's on the receive side? Because we want to make sure we can detect the signal. So that's why the receive antenna is important. Jammer transmitter power. It's 200 watt jammer because people like to talk about how powerful is the tube. So that would include, that's the power delivered to the antenna terminals. The jammer antenna terminals. So that would have to include all the path losses all the way up from the transmitter to the antenna terminals, whatever they are. Right now, it's folded into the antenna, into the transmitter power. So that's something to remember. Pulse width. Well, if it's anything bigger than the PRI, it's CW. Okay, so that covers like a lot of these things here. Target model. If we click on the ship, up comes another form. Okay, well, we have different kinds of ships. There's a frigate, a supertanker, aircraft, a chaff cloud, an active decoy, a passive decoy. But if you pick one and click Create Default, it'll set it up for that. If we want to do, for example, a supertanker, a big one, and click Default, watch the peak intermediate, the intermediate RCS. Those will all change. Treat target as multiple emitters. What does that mean? Well, we need another graphic here. A ship is, we call it a distributed target. multiple reflectors distributed over the superstructure. You don't need more than about 10 scatterers to represent a ship. I mean, you can try it. You can go up to 30 as of them. Try 1, 2, 3, 4, 5, and you'll see the RCS plot, which we'll look at in a few minutes. You see the RCS plot change. And once you get to 10, it's really not changing very much. I mean, it changes, but its characteristics don't change. So all you're doing is chewing up processing time for no benefit. So here we have, this is from the big book, where the scatterers are physically. If we represent the ship as scatterers, what that means is that the seeker antenna pattern is only calculated once. It's as though all the scatterers are sitting on the same line, the same bearing. We only need the seeker antenna pattern once. But if they're spread out in angle, when they're represented as emitters, like each is like its own little mini ship, then we have to calculate the antenna pattern for every single one of those reflectors. Very time consuming. And it would look like this. See how each emitter comes through the antenna pattern at a different angle? The reason for doing that, this one here, which let's say it's a higher fidelity model, that gives you something called glint. Does everybody know what glint is? If you don't, tell me, I'll give you a thumbnail. Glint? Glint. When a missile looks at a ship, it doesn't see what we see with our eyeballs. Ships twinkle. You know, the aim point of the seeker moves around according to how all the scatterers interact at the seeker antenna. Missile designers found this out right away. Like, we're tracking a ship, but look at the aim point of the missile. It's moving, it's dancing all over the place, like a random. And even the aim point can move outside the physical bounds of the ship. That's not very good if you're trying to hit something. Like, the missile might fly like this and wander away at the end. There went an expensive trial, and we can't sell it, the product. So glint is a kind of naturally occurring angle deception countermeasure. It's a property of the physics. You know, you end up, it's basically a cross-eye effect, which I can show. I don't think anybody else has, but that's what it is. So all you need to know is, if you represent this ship as a bunch of scatterers, each one coming through a microscopically different angle in the seeker antenna pattern, that is enough to cause the aim point of the missile, the seeker antenna, to wander around while it's approaching the ship. Remember, this is a game of inches, so the length of each one of these paths determines the phase of the reflection at the receiver. And since it's one wave that went out and got reflected from them all, they're coherent, which means they interact, they do constructive and destructive interference back at the receiver according to what all those path links are. So, and that's where glint comes from. We can have a longer discussion about that. I'd be delighted sometime, but this is the main reason between these two models. With this one, it still takes into account all the path differences. So they do, like, all those path differences are the same, but they come through the same angle in the seeker antenna pattern. So what you get with this model is scintillation. Scintillation means amplitude fluctuation. So this model here, this like less time expensive one, will cause the ship to scintillate in a realistic way. You know, that the skin echo will brighten and dim as the missile flies in. This one here will do the same thing, but also the angle position, the instantaneous target position, will wander around, and that's what glint is. And by the way, the only way of solving the glint problem for the missile designers was to dial down the angle servo bandwidth of the missile seeker antenna, make it sluggish so it can't follow the target. Really simple solution. Just make it slow. But that means that the error voltage which should be driving the seeker antenna doesn't get zeroed out. So if you want it, it's a very powerful target discriminant. If you have a missile seeker staring at a ship and it sees fur on its error voltage, that's a ship. But point sources don't do that. Decoys don't. They don't glint. So if it looks at a target and it says a totally quiet or a very quiet error voltage, that means that's a decoy. Not interested, reject it, go back to my third, range and angle tracking memory and start tracking that. Let's move back onto something else. Reject the decoy. So this is why we're interested in studying this and knowing about it and having a model for it. As far as I know, Engage is the only model, the only one I know of, that has glint from first principles. The rest of them have it, oh yeah, that's, we went out and studied. You would put in like maybe a statistical model. So if it's tracking the ship, we switch in a statistical model that adds noise to the error voltage. But this one comes from first principles. Anyway, not to get dragged down that rabbit hole any farther than I already have, but that's the important meaning of treat as multiple emitters or as scatterers. So, you know, you have the option of using broadside flashes or not, and we, you know, if you look it up in the book, you can see what's in there. And there's a little, let me close this. Let's stick with the supertanker. Create default, yes. And I'll click save. And I close this. And there's a summary here, so you don't have to keep pulling up this thing. You can, this is a summary of what's on that form, so you don't have to go looking for it. Do we want to turn the emitter motion on and off? Yes, we can. Turn it on or turn it off. Is the ship stationary? So it's got a speed. Here it is in meters per second, but this little label shows you it in knots, because quite often we want to talk about how many knots something's going. So who wants to take out their calculator and figure that out? Go back and forth. So if we wanted, you know, 20 knots, we would go down to, I'm just looking at this label while I ignore this thing. There's 21.4 knots. There's 19.4. Heading, the missile heading, 45 minus 45 degrees, change that. Heading rate, it can be turning. And then there's a start time and a duration for the motion. But we don't want to do that. So anyway, with all that, why don't we just do a run and see what happens? Oh no, we haven't talked about missile initialization. Up here in the top right. We can give the missile a target. The targets are numbered 1, 2, 3, 4, 5. And if you set it at 0, there is no target. What that means is at the start of the engagement, the missile doesn't know what's there. It'll do a range search. If it doesn't find anything, it'll do a volume search. I mean, an angle search and a range search at the same time. But you have to design those yourself. And the default is right, I think. But if you wanted to choose your angle sweep and range sweep, you have to get enough power on the target, so you can't be sweeping too fast. You don't want to sweep so that the half power beam width of the seeker moves faster than the range gates can sweep, right? So you'd have, that's the thinking part, the missile designer part. So if there's no target, it does an angle search and volume search to find something, and when it finds something, it behaves in a normal way. If we do give it a target, like target number 1, in this case, that means the range gate and the seeker, this range gate is positioned on the target at the start of the engagement, and the seeker is pointing at the target, no matter how you set it up. So this is like least favorable to the jamming. So I think that's kind of an interesting way to go. We can change the cross-range position of the missile, and we can give it a heading error. So if you wanted to see, like, is this missile model, does it work? Can it hit something? Well, don't put a beacon on board, or just a ship. Like, you can blank the transmitter and make sure the ship is present. If you do this, you get volume search all the way in. It never finds anything. There's no transmitter and there's no ship. You click load. So yeah, so okay, so that takes care of the, like, what the missile is doing, where it is and where it's headed. This box here has to do with noise. So if we click this checkbox, we enable missile body roll. So it's a heuristic. There's no roll autopilot. There could be, but there isn't. So this just adds band-limited noise to the roll position of the missile. That's important for cross-pole jamming, because if there's roll noise, will couple to the cross-pole program. And we would want to see how that happens. So how do we design our countermeasures to accommodate a rolling missile? Now, missiles don't roll. None that I know of roll to turn. They're all skid to turn. And the reason is because the autopilot model or design becomes horribly complex, because the elevation it has with autopilots are now going to couple into each other, and you don't want to get into that. And we also can do the same thing with the body, the other two axes, like yaw and pitch. So, or yaw and climb. So if we use this radio group from off, now we have body yaw noise, and now we have body pitch noise. I could have made a button for both at the same time, but it just didn't do it. So yaw noise, why would we want to do that? Why would we? What that means is the missile is going to fly toward us, and it's going to randomly jink left and right at whatever bandwidth and amplitude in degrees that we set. Why would we want to do that? Well, suppose we were looking at a passive range estimator, and we wanted to know how reliable is this thing as the missile flies in while we're jamming it. Suppose we are successful, we're causing the missile to develop a heading error. Well, the radial missile velocity changes, so that'll affect the range estimator, but how much? Well, one way of studying that is to develop some sort of a countermeasure engagement model where we actually do cause the angle errors, the flight trajectory deviations to happen. But that's a lot of work, and it's tricky, and you're only going to get one kind of deflection. So a better approach would be to allow the user to put in random noise and control that in bandwidth and amplitude, and then do a bunch of runs and explore its properties that way.